All right, so let's get started with lesson 3. And as I promised in the intro video, we're going to be defining some patterns that we can use repeatedly when we try to take derivatives that will keep us from having to really write out the whole limit solving process every single time. These patterns or these formulas are going to give us the opportunity to memorize the pattern and then just see it in a formula and be able to give an answer almost immediately, especially for these basic ones, which is what we're going to cover. The first 4, which is what we'll talk about in topic 1, they're going to be the ones that are easiest to solve. So, that being said, pull out your notebook, and since we have 4 formulas that we're going to talk about, or 4 patterns that we're going to talk about, patterns of differentiation, why don't you write numbers 1 through 4. And the first one we're going to talk about is, of course, we're talking about derivatives, so we're going to use the symbolism, d dx. That means performing the operation of taking the derivative. We're going to say anytime we perform this operation, anytime we take the derivative of c, now what does c mean? Well, anytime in algebra, really, if we use the letter C, we almost always mean just a constant term. So a number. It doesn't matter if it's 1 or 10 or -2, 1.5, the number pi, 1/4. If it's a number and just a number, then it's a constant. So anytime we take the derivative of a constant, the answer will always be 0. That's the first rule. Don't you love answers that are just always 0? So if you take the derivative of a constant, the answer is always 0. And what does that mean graphically? Well, over here I have 3 different functions that are examples of constants. We have first y equals 3, and there it is. Then I have y equals -2. There it is. Y equals, oops, let's see if we can highlight that. There we go, 1.4. So 3 different examples. Constant functions. They're about as boring as they get. As you see in each example, f, g, and h, they're all flat, right? Because that's what constant functions look like. So what is the slope of any position along a constant function? Well, it's always 0, right? It's always horizontal, so it's always 0. So is it reasonable to create a rule here that says the derivative of any constant value is always 0? Yes, we say that is reasonable. It makes sense. Okay, next rule. I like this one a lot. This is called the power rule. So if I'm taking the derivative with respect to x of any function that fits this pattern, x to the power of n, so that could be x squared, x cubed, x to the 5th. It could actually even be x to the -5th or x to the 1/4. This actually works for any type of power function, whether it's rational, if it's rational, positive, negative, whatever. Okay, so any power function, if we take the derivative of x to the n, the derivative will always be n times x to the n minus 1. Okay, I'm going to show you what that means on a separate screen here, so you can see that probably looks like nonsense, but let me show you what that means. Let's create a derivative ladder, and we'll start with y equals, let's say, x to the 4th. And we're going to take the derivative a few times. This fits our power rule because x to the 4th is a power function, right? So the power rule says if you want to find the derivative, what you do is you take the power, you swing it out to the front, and then you drop the power by 1. That's what we're saying here. Take that number that was in the exponential spot, swing it to the front, turn it into a coefficient basically, and drop the power by 1. Subtract 1. So in this case, that would say that the derivative should just be 4x to the third power. So just instead of the fourth power is the third, and that number 4 kind of swings out to the front, and that's the derivative. That's it. Isn't that a beautiful thing? Watch how easy this is to keep the process going. Let's say we don't want just y prime, which remember is the first derivative. What if we want the second derivative? So we're just going to do it again. Let's find the derivative of the derivative. No limits, no writing out all these numbers. We're just going to use the pattern. We say, does this still fall into the pattern of being a power function? And we're going to say yes. All we need to do is take that 3, swing it out to the front, and drop the power by 1. Well, if I swing 3 out to the front as a coefficient, I'm going to have 3 times 4. So now I'm going to have 12, right? 3 times 4 is 12. And then the power drops to 2. Swing that number to the front, drop the power by 1. Okay, let's do it one last time. We're going to find y triple prime. Does this fit the pattern of a power function? Yes, it does. Do I need to use limits to solve this? No, because I know the pattern. I say this has a power of 2. Let's swing this to the front as a coefficient. So now I'm going to have 2 out front. 2 times 12, well, that makes 24. And now I have x to the power of 1, which is really just the same as x. Right? I don't really need to put the power of 1. 24 times x to the first power, because I dropped it down, so 24x. And I could continue this on, because actually x is still a power function, right? Actually, maybe I should, because that's a good last hurrah here. We'll find y to the fourth prime. This is x to the first power, so it still fits the pattern. I still don't need to go back and use limits. Swing that 1 to the front. Well, 1 times 24 isn't going to change anything. And now that x is x to the 1 minus 1, x to the 0 power. Well, anything to the 0 power is just 1. Or x to the 0, anything to the 0 is just 1. So this becomes 24 times x to the 0, or 24 times 1, or really just 24. And so we have managed in 1, 2, 3, 4 derivatives to turn x to the 4th into just a constant. And that's what happens when you take derivatives of derivatives of derivatives. That is an example. That series of derivatives is, I was able to do 1, 2, 3, 4 problems very quickly because I just used this pattern. If it's a power function, you bring the power to the front as a coefficient, and then you drop that power by 1. And actually, remember, if it was a negative, so if it was like to the negative 5, you would drop it by 1, which would make it negative 6. So just make sure you follow that rule literally. It wouldn't go from negative 5 to negative 4. That's not dropping 1. That would be increasing by 1. So if it was the power of negative 5, it would go down to negative 6. Okay, that's the second rule. Third rule is I actually just did it without telling you, and you didn't even realize it probably. So let me show you what the third rule is. And actually, you know what? I'm looking at this and realizing I am going to run out of room. So let's do 3, and then we'll do 4 down at the bottom. Okay. So rule number 3, which we've already technically done without realizing it, says that if I want to take the derivative of any function, so let's, instead of defining what the function is, let's use the letter u, which is in calculus one of our most favorite letters to use to describe some function of x that we want to keep really abstract. So it could mean x squared, it could mean sine of x, it could mean 1 over x. It's just some function with respect to x, but we're going to keep it vague by calling it u. So if we have a function, u, whatever that is, and we decide to multiply it by a coefficient, so here comes c again, we're going to take some function, multiply it by a coefficient, a constant value c, although it's not really a constant here, it's a coefficient, it's multiplying. Then all we have to do is figure out what the derivative of u is. So we could call that, actually let me do that, I'm going to call it u prime. So the derivative of u would be u prime. We don't need to know what it is right now. But if we have a function, we multiply it by a number, then we can easily find any scaled value of that function. So you find u prime, and then you just multiply the answer by that value c. So let's go back to our example here. Technically, when I was finding the derivative of 4x cubed, I was using this rule because I was actually using the power rule to figure out what x cubed was. And I was just assuming that it was okay to carry this 4 through and not really worry about it too much. Like the 4 just carries through, and then the 12 just carried through. I didn't have to derive 12 separately because it was a coefficient. It was just scaling the function. And that's what this third rule means. It's not really a standalone rule. It's just saying if you're multiplying, if you know how to derive x squared, then you know how to derive 3x squared. It's just going to be 3 times bigger. If you know how to derive x squared, you're also going to know how to derive 10x squared because it's just going to be 10 times bigger. So that's what that third rule is talking about. All right, last but not least, this one is just about as simple and straightforward as number 3. And it says, if we want to take the derivative of 2 different functions. So last time I called a random function u. Well, when we need to have more than one, we usually use v. So we'll say if I have u and I have v, 2 different functions. It could be x squared and x cubed. It could be sine of x and tangent of x. They're just 2 different, they could actually both be x squared and x squared. They're 2 different functions, or the same functions, 2 functions with respect to x that we're going to leave ambiguous and unknown. If I am adding those 2 together, or if I am subtracting them, so if I have 2 functions and I'm either adding or subtracting them, I am allowed to derive them separately and just add later. So we would say it's okay to derive, or actually, you know what, I'm going to use the u prime, v prime. We can just derive u, that'd be u prime, derive v, that's v prime, and then we either add or subtract them depending on what we're doing. So here's an example. Let me go to my other one here. We're going to clear. Let's say we had the derivative of x squared plus x cubed. What this last rule is telling us is that it's okay to just derive x squared. Let's use the power rule. Swing the 2 to the front and then drop the power by 1. So it's going to be 2x to the 1, or just 2x, right? We don't need to write 1. So check, we did that. This rule says I can then also go to x cubed. Forget about x squared for a moment. X cubed is same thing. We can swing the 3 to the front, 3x, drop the power by 1, squared. 3 to the front, 3x squared. So I found this one, and I found this one, and the rule says whatever is happening, we're adding here, we just add that to our answer. And this is our answer. That's it. Kind of intuitive, right? So the last rule says you can just derive them each separately as long as it's just addition or subtraction. Notice it's not saying multiplication, it's not saying division. Those have their own rules. But addition or subtraction, we're allowed to derive separately and then just stick them all together at the end. Derivative of a constant is always 0. Derivative of a power function, you swing the power to the front and drop the power down by 1. We can also scale a function, and it just scales our answer. So if you're multiplying by 5, it just multiplies our derivative by 5, so that's nice and easy. And then lastly, our 4th rule was you can add or subtract different functions, and you can derive them separately and just add them together at the end. Okay, those are our 4 basic rules, and we will stop here for topic 1, and then in topic 2, I'll add on rules 5 and 6, which have to do with multiplication and division, and those are going to require just a little bit more time to solve. They have a few more steps than these original 4. All right, that is it.